Okay, Chapter 1, Algebra 2 book. Sets of numbers. So we're going to be talking about all of the different sets of numbers today, first of all, and looking at classifying and ordering real numbers. So some vocabulary stuff here. So a reminder, a set is a collection of items called elements. Okay. So how many of you play pool? Okay. All right, so on a standard pool table, there are 15 balls on that pool table. There are ones that are solids, like blue, orange, green, that are the numbers 1 through 7. There's the 8 ball, which is black, so that's kind of a solid. And then there are the numbers 9 through 15 that are striped, so they have a colored stripe through the middle, and then they're white. The rest of the ball is white on each side. Okay. So there are 3 subsets of the pool balls. There's the solids, the stripes, and then the 8 ball. Okay. It's always better to not be behind the 8 ball. That's just not a good thing. Okay. All right. Especially when you're down to a team and they won't let you have the ball back. Okay. Right, Nolan? Nathan? What? Okay, so a subset is a set whose elements belong to another set. So like the solids are a subset of all of the billiard balls. And the empty set, which is a circle with a line that goes kind of diagonal through it, is when there's nothing in that set. So if I asked you what was the set of checkered balls for the billiard balls, which there is no checkered balls, so you would say that would be the empty set. So you would put a little circle with a line through it like that, means the empty set. This picture here shows all the different types of numbers that we deal with in mathematics. Close to it, okay? It doesn't show imaginary or complex numbers, but this is for the real number system. For real numbers, there are 2 major subsets under the real numbers. There are rational numbers, which are represented by a Q, and then there are irrational numbers. Rational numbers can be written as a fraction or a decimal that terminates or repeats. Okay, so like 0.333 with a bar over it. Okay, that would be a rational number because it terminates or it repeats, because it repeats over and over again. So the number 3.5 would be a rational number because it terminates. Right? Irrational numbers are like anything that involves a square root that you can't find the square root of. So the square root of 37 would be irrational, but the square root of 36 would be rational, because the square root of 36 is 6. Okay? I also include in that are pi and e, which is the natural base, which is something you'll learn more about when we get to chapter 7. Okay? Under rational numbers, there are other subsets. Integers, which are represented by the letter Z, are positive and negative whole numbers. So 1, 2, 3, 4, 5, 0, negative 1, 2, 3, negative 85, negative 400. Those are integers. Whole numbers are integers that start at 0, represented by a W. And then there's the natural numbers, is the smallest subset. So they have the natural numbers, which start at 1, 1, 2, 3, 4, 5, 6, and so on. And then whole numbers are all the natural numbers plus 0. Integers are all the whole numbers plus the negative ones. Okay, so positive and negative whole numbers is sometimes the way it's referred to. And then rational numbers include all of those plus anything I can write as a fraction. So if a decimal terminates or repeats, it can be written as a fraction. So they would be a rational number. And then we have irrational numbers. So note the specific symbols. R for real, Q for rational, Z for integer, whole, W for whole numbers, and N for natural numbers. Now you can write the whole word out if you want, or you can use the symbolism. Okay? The one that's used more than anything else usually is the one for real numbers. And for real numbers, I use that, looks like that right there. Does anybody know what that looks similar to? How many of you have ever seen this symbol here? How many of you have seen that symbol there? Okay, Mitchell, what does that symbol there stand for? Okay, paragraph, right? You've seen it as a paragraph, okay? Symbol. So the symbol for real numbers is just like the paragraph symbol, except it's an R instead of a P, okay? Thanks for playing there, Wolverine. Okay? All right. I don't know. Like Sesame Street? Okay. All right. So we have rational numbers. Write them as fractions. So here we have the rational numbers. The decimal form of a rational number can either terminates or repeats. And if it's an irrational number, then it just goes on and on forever. Okay. Oh boy. Okay. So we're going to do, first example here, we're going to order and classify some real numbers. So we have these numbers, 2.3 with a bar over it, over the 3, pi, square root of 5, negative 11 halves, and 2.7652. So we're going to order these numbers from least to greatest, and then we're going to classify them according to which system they belong to. So we're going to order them from least to greatest, and then classify them for which number system they belong to. So one of the easiest ways to put your numbers from least to greatest would be to write them as decimals first, if you can, so that you can see them that way for ordering them from least to greatest. So let's change these so that they are all decimals. So we have 2.3 with a bar over it. Pi is what? 3.14. Okay. Square root of 5, what's that as a decimal? 2 point something, right? Is it 2.23? Okay, so 2.23 will help us. And what about negative 11 halves? What's that? Okay, negative 5.5. All right, and then we have 2.7652. Okay. So, which one of those numbers is the smallest? No, there's only one negative number, right? So that has to be small. So that's negative 11 halves. Okay. All right, now what? So we have, so we got 2.3 with a bar over it, 2.23 and 2.7. Okay, 2.23, which is the square root of 5, right? Okay. So when I order them from least to greatest, I'm going back to their original, not as their decimal. Okay. All right, then what? Okay, 2.3 with a bar over it. And 2.7652. Oops. And then our good friend pi. Okay. That one guy named Pi.
It's like some guy that like fall off the ship and like goes past like an island or something. I don't know, it's like they're called like that.
And he has used the 500th digit of pi to be able to get home. Okay, so as Matt said earlier, he's just kind of going off in la-la land. So let's pull us back on task here. Okay, 2.3 with a bar over it. So first of all, we have real numbers. So I made this little chart, and whether you make the chart or not is up to you. You can just put the letter down or the number down and then write what it goes with. So 2.3 with a bar over it. So first of all, they're all real numbers. Okay, we don't have any non-real numbers. Okay, rational numbers are if we can write them as a fraction, which means that they're either written as a fraction already, or they are terminating or repeating decimals. Okay, so does 2.3 with a bar over it, does that have, okay, that's a terminating, no, that's a repeating decimal, right? Okay, so that's a rational number. Is this an integer? No, it's not an integer. An integer would be like 1, 2, 3, 4, 5, or negative 1, 2, 3, 4, 5. So if it's not an integer, it's not any of those other ones either, is it? Can't be whole or natural. Okay? Pi. Is pi a rational number? No, pi is irrational. Square root of 5, is that rational? Can you write it as a decimal that terminates or repeats? For sure, yes. Actually, the only way you can do that with a radical is if it's a perfect square. Okay, so this is irrational. Square root of 5. I know I'm good. Okay, negative 11 halves. Is that rational? Okay, it's a fraction, so it is rational. Okay, but fractions are not integers, are they? No. Okay. All right. 2.7652. Is that rational? Yes, it is. Because it terminates. But it's not an integer, so it's not whole or natural. So you could either make this table when you're answering these questions, or you could just write down the number and say, okay, so I had the number 2.3 with a bar over it, and that number is real and rational. Okay? Or you could just write real and rational. Okay? You can do it however, whichever of those three ways you want. Make a table and do that. Write down each separate one. It's up to you. Okay? Okay, now, the next two things we're going to look at is going to be notation of ways of expressing sets of numbers. Okay? One of the ways to express sets of numbers is called roster notation. And with roster notation, we use braces and we list all of the elements separated by commas inside the braces. So for instance, we had the set of billiard balls. The billiard balls are numbered from 1 through 15. So if I have roster notation to do that, I would put braces on the outside and then the numbers 1 through 15 separated by commas on the inside. Right? If we had the numbers 1 through 5. Okay? Then we just list them 1, 2, 3, 4, and 5 with braces around them. Okay? A set can be finite, like the billiard balls, okay? Or it can be infinite. So an infinite set would be here, like the set of natural numbers is an infinite set because it starts at 1 and goes on forever. Okay? So we would have in braces then the numbers 1, 2, 3, 4, and dot, dot, dot. Okay? So it means that it goes on forever. Okay? A finite set has a definite or finite number of elements, where an infinite set is unlimited. A lot of infinite sets cannot be represented by roster notation. For instance, rational numbers cannot be written as roster notation because there's so many of them you couldn't list them all. Like what we can for like the natural numbers or whole numbers. A set of real numbers between 3 and 5, which is also an infinite set, can be represented on a number line or by an inequality. So here the numbers between 3 and 5 are listed on a number line, and here they're written as an inequality. So on the number line we would have open dots, which mean what? What do open dots mean on a number line? Okay, so it means there's no line under here. Okay, all right, that's one thing it means. But what else does it? What does it truly mean? So how about if we say it this way? It does not include that number. Okay, all right. So it means I'm starting at 3, ending at 5, but it doesn't include them. In other words, it could be 3.000000000000001. Okay, is that bigger than 3? Yes. And the number 4.99999999999999999. Is that smaller than 5? Yes. Okay. So the numbers between 3 and 5, not including them. And we represent them on an inequality by saying just greater than and less than. Okay. Well, there's another way of representing numbers, and it's called interval notation. And interval notation uses either brackets or parentheses for the endpoints. So for instance, our number here on the number line from 3 to 5, or x is greater than 3, less than 5 as an inequality, in roster notation would be parenthesis 3 comma 5 parenthesis. When we're talking about interval notation, in interval notation we use parentheses if it does not include the endpoints. We use brackets if it does include the endpoints. So if we had, oh, here I got them down here. So an interval that extends forever in a positive direction goes to positive infinity. Negative direction goes to negative infinity. So here are some representations here, how everything is done. In words, if I have the numbers less than 3, in a number line, we'd have an open dot on 3 and the arrow going to the left. As an inequality, we would say x is less than 3. In interval notation, then, we would have parenthesis, negative infinity, comma, 3 parentheses. Whenever you do interval notation, the smallest number is always on the left. The largest number is always on the right. Whenever you write an inequality, the smallest is always on the left, the biggest is always on the right. Okay. Now look at the second part here. Okay. Numbers greater than or equal to -2. So because it includes -2, because it's equal, we put a solid dot, arrow going to the right. So as an inequality, we'll say x is greater than or equal to -2. And then in interval notation, we'll have a bracket there next to the -2 because it includes -2. And then comma, parenthesis or infinity and then parenthesis. Now, is infinity an exact number? No, it's not. So that'll always be a parenthesis for infinity because it's not exact. Okay. Right. Notice in the last one says numbers between, or the third one says numbers between 2 and 4, that you always list the smaller number first. Okay. Smaller number is first here, smaller number first here. Down at 1 to 3, smaller number than the larger number. Always list them in that order. Some people tend to get that mixed up and put the larger number then the smaller number. Don't do that. It's always the smaller number, then the larger number, just like you would on a number line. Okay. Now, I saw somebody doing this the other day where when they put stuff on a number line, they didn't put it right on the number line. They put it above the number line. Don't do that. Okay? It goes on the number line. Okay? Not above it. Okay? All right, so they want us to use interval notation to represent these sets of numbers. So when we're using interval notation, we always put the smaller number, then the larger number separated by commas. If it includes a number, we use a bracket. If it doesn't include a number, we use a parenthesis. So does this include 7? No, because there's not a line under the greater than. So that means it's a parenthesis. Does it include 12? Yes. So that means it's a bracket. Okay. So we have the numbers from 7 to 12, not including 7, but including 12. That's a bracket. This is a brace, and that's used for roster notation. Okay? You only use the brace when we're talking about roster notation. This is a bracket that's used for interval notation. Okay? Okay. Letter B. Now here we have 2 different parts. Okay? So we have to represent those 2 different parts, and we'll represent the 2 different parts then with the word or. So anytime there's a gap on a number line, then you're going to use the word or for separating them. So we have from -6 to -4, or we have from 5 to infinity. Okay? So from -6 to -4, it includes those 2 numbers because it's solid dots, so I use brackets. From 5 to infinity, it does not include the 5, so I use a parenthesis, and it never includes infinity is not an exact number, so we always use a parenthesis there. So -6 to -4, including them, or 5 to infinity, not including 5. Okay? That's roster notation. So here they showed an inequality and then roster notation that goes with it. Here a number line and roster notation that goes with it. Okay? Not interval notation, excuse me, interval notation. You're messing me all up there. Matt's got me messed up today. Okay? All right? So inequality, you're using less than, greater than symbols. You guys should all know how to do number lines. And then we have interval notation if we are using brackets and parentheses. And we would use braces if it's roster notation. And for roster notation, you list all the different numbers. Okay. All right. Okay. There's one other type of notation, and it's called set builder notation is how it's referred to. Now, we're not going to do it quite exactly the same as what they have here, okay? But we're going to look at it similar to that. Because really when we're doing, our notation is basically going to be using inequality notation, and that's basically what set builder notation is. is using inequalities. It just involves a little bit different thing. So here it says, this means the set of numbers, that's when I use the braces, I say the set of numbers, x such that, that little straight line there is such that, x is greater than 8, less than or equal to 15, and x is an element or a member of the natural numbers. So here they've got the numbers 9, 10, 11, 12, 13, 14, 15. And they use this notation to do it. Now, here's the thing. If I was you, okay, with a situation like that, all you would need to do is say that x is be greater than 8, less than or equal to 15, or you could say that x is greater than or equal to 9, less than or equal to 15, and the natural numbers. Okay, natural numbers. Right. You wouldn't have to list it exactly that way. So here they have a table here with all the different things: words, roster notation, interval notation, set builder notation. Okay. So translating between methods. Okay. So if we wanted to use these numbers here, it says this means x such that x is greater than negative 5.5, where x is an element of z. What's z stand for? Which set of numbers? Integers, okay? So what does this mean in words? What does it mean in words? It means the integers that are greater than negative 5.5. Okay? Integers greater than negative 5.5. So that would be negative 5, negative 4, negative 3, negative 2, negative 1, 0, and so on. Okay? Yep. Okay, so what does this say? This tells me that we're dealing with integers that are greater than negative 5.5. Can be. All right. Letter B, positive multiples of 10. Positive multiples of 10. All right? So what are the multiples of 10? Alex, what are they? Multiples of 10. Not factors of 10, multiples of 10. All that good stuff? What is it, Nolan? Since 10, 20, 30, 40, okay. Right. So if I'm using roster notation, then I'm going to use a brace. So it would be braces. And then we'll do 10, 20, 30, and you can list as many as you want, but then we're going dot, 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 because I can't list them all, can I? Okay. All right. I know you were. Okay. Can't list them all. You keep doing it in your head, okay? We'll tell you when you're done. Letter C. When it says to do something in set builder notation, just write it as an inequality. So this is the inequality where x is less than or equal to negative 2. All right? No, you're supposed to put it on my desk. The whole thing. Okay. So when it says to do set builder notation, just write it as an inequality, because that's actually all it is with just a little extra stuff there. So if it says set builder, just give me the inequality that goes with it. Okay. All right. We're running out of time.